Before there was light, before there was time, there was nothing. But from that nothing came everything. A massive explosion gave birth to the universe, and what followed is the most mysterious story ever told. From the unimaginable fury of the Big Bang to the silent devourers of space called black holes, today we dive into the secrets the cosmos has kept hidden for billions of years. Backhand index pointing right. Subscribe to History Vault now, because the universe is speaking and we're here to decode it. 13.8 billion years ago, something unimaginable happened. There was no light, no space, no time, just a singularity. Then, in a moment that defies all understanding, the universe began. It wasn't an explosion in space. It was the expansion of space itself. This was the Big Bang, the very moment everything came into existence. From this singularity emerged all matter, energy, and the fundamental laws of physics. There was no before, because time itself began here. In the first trillionth of a second, the universe expanded faster than the speed of light in what scientists call inflation. It was unimaginably hot and dense. Particles didn't even exist yet. But within microseconds, fundamental particles like quarks and electrons began to emerge. As the universe cooled, quarks joined together to form protons and neutrons. Within minutes, nuclear fusion created the first atomic nuclei, mostly hydrogen and helium. But light still couldn't travel. The universe remained a hot, opaque fog of particles. For 380,000 years, photons were trapped, constantly scattering off charged particles. Then, as the universe cooled further, electrons combined with protons to form neutral atoms. This allowed light to travel freely for the first time. That ancient light is still traveling through space. It's called the cosmic microwave background, and it's the oldest light we can observe. This evidence, along with redshift observations of galaxies, confirms that the universe is still expanding today. When astronomers observe distant galaxies, they see that their light is stretched or redshifted. This stretching reveals that galaxies are moving away from us, and the farther they are, the faster they recede. It's not that galaxies are flying through space. It's space itself that's growing. This discovery shook science to its core and supported the revolutionary idea that everything had a beginning. The Big Bang theory is not without mysteries. The most profound is, what triggered it? What existed before time began? Our current physics breaks down at the singularity. General relativity, which describes gravity, and quantum mechanics, which governs the smallest particles, cannot yet be unified into a single theory that explains this moment. Scientists call this the quantum gravity problem, and is one of the biggest unsolved puzzles in physics. Several theories try to answer this. One is a multiverse theory, the idea that our universe is just one of countless others, each with its own laws and constants. These may have bubbled up from a quantum field, or branched off from other cosmic events. If true, it would mean the Big Bang was just a local event in a much larger, eternal system. Another theory suggests the universe goes through cycles of expansion and contraction, what's called a cyclic universe. In this model, our current expansion might eventually reverse, collapsing everything back to singularity, which then triggers another Big Bang. This eternal cycle could mean there was no true beginning, just endless rebirths. There's also the quantum fluctuation model, where the universe spontaneously emerged from a quantum vacuum, a field that appears empty but teems with energy. According to this theory, nothing is truly nothing, and the laws of physics allow the universe to arise without cause. It's counterintuitive, but quantum physics often is. Stephen Hawking and James Hartle proposed another idea, the no-boundary condition. They suggested that time itself may have once been imaginary, like a spatial dimension. According to their model, time became real only after the Big Bang, so there's no before in any meaningful sense. Despite these theories, the truth is we don't know. But what we do know is already astonishing. From a moment smaller than a fraction of a second, everything we see today came into being: galaxies, stars, planets, and eventually life. All of it came from a single moment of creation, governed by laws we're still trying to understand. And even more mind-blowing, we are part of the story. Every atom in your body was forged in this unfolding of the cosmos. The hydrogen in your water, the calcium in your bones, the iron in your blood, all originated from that first burst and the stars that came after. You are literally made from the dust of the universe. The Big Bang isn't just a scientific theory. It's the beginning of our story, a story still unfolding with every star that is born, every galaxy that spins, and every question we ask about where we came from. It connects us to everything in existence and reminds us that from nothing came not only something, but everything. Since the moment of the Big Bang, the universe has been expanding. This isn't just galaxies moving through space. It's a stretching of space itself. Imagine dots on a balloon. As the balloon inflates, the dots move away from each other not because they're moving, but because the surface they sit on is growing. That's what's happening to the universe. Everything is getting farther apart, and there's no center. Every point in the cosmos sees everything else moving away, which was one of the most startling revelations in the history of science. Edwin Hubble was the first to notice this in the 1920s, when he observed that galaxies were receding from us, and the farther they were, the faster they seemed to be moving away. This became known as Hubble's law. It led scientists to realize that the universe is not static, as once believed, but dynamic and constantly expanding. This expansion has not stopped, and even more surprising, it's accelerating. This acceleration isn't caused by gravity or matter, but something even more mysterious, a force we call dark energy. Dark energy makes up roughly 68% of the entire universe, yet we have no idea what it actually is. It acts in the opposite direction of gravity, pushing galaxies away from one another. It's like an invisible pressure stretching the very fabric of reality. Some scientists believe dark energy might be a property of space itself, while others think it could be linked to quantum fields or dimensions we cannot perceive. Whatever it is, it dominates the cosmos and determines its ultimate fate. This cosmic expansion also raises profound questions. Is there an edge to the universe? Can we ever reach it? The truth is, the universe might not have an edge at all, not in the way we imagine. If space is infinite, then it just goes on forever. But if it's finite, it may curve back on itself like the surface of a sphere. You could travel in a straight line and eventually return to where you started, though it would take longer than the age of the universe to do so. Even more puzzling is what lies beyond the observable universe. Due to the finite speed of light and the age of the universe, we can only see a small fraction of the entire cosmos, about 93 billion light-years across. Beyond that, space may continue infinitely, filled with more galaxies, more matter, and perhaps even more laws of physics. The edge of what we can observe is not the edge of the universe. It's just the limit of what light has had time to reach us since the Big Bang. Some scientists even speculate that our universe is just a bubble in a vast multiverse, a sea of countless other universes, each with different physical laws and constants. In this scenario, our universe could have pinched off from another in a quantum event, just one bubble in an eternal cosmic foam. Though this is still theoretical, the math behind it fits within models of inflation and quantum cosmology. If true, it would mean we are part of something far grander than we can imagine. Cosmic expansion also affects time. As the universe expands, the light from distant galaxies becomes stretched, shifting toward the red end of the spectrum. This redshift not only shows us that space is expanding, but also allows us to look back in time. When we observe distant galaxies, we are seeing them as they were millions or even billions of years ago. The further we look, the younger the universe appears, offering us a time machine powered by light. But this expansion won't last forever in the same way. Depending on how dark energy behaves over time, the universe could meet one of several fates. It could expand forever, growing colder and more isolated. It could slow down and reverse, ending in a big crunch. Or dark energy could grow stronger and tear the universe apart in a big rip. Each outcome is shaped by the mysterious properties of space itself. In the end, the story of cosmic expansion is a story about change. From a single moment of creation to an ever-stretching cosmos, the universe is a dynamic, restless place. And even though we live on a tiny planet around a tiny star in a quiet corner of one galaxy, we are part of this enormous unfolding. Every second, space itself is stretching all around us, carrying galaxies, light, and time forward into an uncertain future. It's not just the stars that are moving. It's the fabric of reality itself. Stars are the engines of the universe. They are not just distant balls of burning gas. They are cosmic factories, forging the very elements that make life possible. Born from vast clouds of gas and dust called nebulae, stars ignite when gravity pulls this matter together, compressing it until the pressure and temperature at the core becomes so intense that nuclear fusion begins. This fusion is what powers a star, hydrogen atoms merging into helium and releasing immense energy in the process. A new star begins its life quietly. For millions of years, it fuses hydrogen into helium, balancing the outward pressure from fusion against the inward pull of gravity. This delicate balance keeps the star stable. As it burns its fuel, the star shines, warming planets and lighting up the cosmos. But this balance can't last forever. Eventually, the hydrogen runs out, and the star must evolve or die. For small stars like our Sun, the end is relatively peaceful. When hydrogen is exhausted, the core contracts and the outer layers expand, turning the star into a red giant. Helium fusion begins, creating carbon and oxygen. Finally, the outer layers drift into space, forming a beautiful planetary nebula, while the core becomes a white dwarf, a dense, cooling ember that will eventually fade into darkness over billions of years. For massive stars, the story is far more violent. These stars burn to their fuel rapidly, fusing heavier and heavier elements, helium into carbon, then neon, magnesium, silicon, and finally iron. But iron is a dead end. Fusing iron doesn't release energy. It consumes it. When a star's core is filled with iron, it can no longer support itself. Gravity takes over. The core collapses in a fraction of a second, triggering a supernova, one of the most powerful explosions in the universe. In this final cataclysm, the star tears itself apart, blasting heavy elements like gold, uranium, and platinum into space. These elements scatter into the cosmos, enriching nearby gas clouds that will one day form new stars and planets. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the heart of a dying star. This is the cosmic alchemy that connects us to the stars. We are not just made of stardust. We are stardust, assembled into conscious form. The remnants of massive stars can become neutron stars or black holes, depending on their mass. Neutron stars are so dense that a teaspoon of their matter would weigh billions of tons. They spin rapidly, emit beams of radiation, and can even collide to create gravitational waves and forge even heavier elements. If the collapsing core is massive enough, it forms a black hole, an object so dense that not even light can escape. Stars are born in cycles. A supernova may destroy a star, but it also triggers the formation of new stars. Shockwaves from the explosion compress nearby gas clouds, causing them to collapse and form new stars. In this way, the death of one star gives birth to another. It's a cosmic recycling process that has been happening for billions of years, building galaxies, planets, and eventually life itself. The Sun, our life-giving star, is about halfway through its life. In 5 billion years, it will expand into a red giant and eventually leave behind a white dwarf. Long after humanity is gone, the Sun's light will fade, joining countless other stars in the cold, dark future of the universe. But the elements it created and the life it sustained will carry on in new forms, perhaps even in civilizations yet to be born. In this grand story, stars are both creators and destroyers. They shape the universe, build the elements, and light the darkness. Without them, there will be no planets, no oceans, no DNA, and no thoughts. Stars are the heartbeat of the cosmos, pulsing across space and time, writing the story of existence with every nuclear fusion and every brilliant death. Black holes are the most mysterious and terrifying objects in the universe. They are places where the known laws of physics break down, where gravity becomes so strong that nothing, not even light, can escape. They form when massive stars collapse at the end of their lives. If the core left behind is heavy enough, gravity compresses it into a point of infinite density and zero volume known as a singularity. Surrounding the singularity is the event horizon, the boundary beyond which no information can return. Once something crosses this limit, it is lost forever to the outside world. What makes black holes so strange is that they don't just exist as dead remnants of stars. Some are millions or even billions of times the mass of our Sun. These are called supermassive black holes, and they exist at the centers of most galaxies, including our own Milky Way. We know they are there because of how they affect the stars and gas around them. Their gravitational pull is so powerful that entire star systems orbit them at immense speeds. Despite being invisible, their presence shapes the structure of galaxies and influences cosmic evolution. One of the most mind-bending features of a black hole is how it warps space and time. According to Einstein's general theory of relativity, mass bends a fabric of space-time. The more massive an object, the greater the distortion. A black hole creates such an extreme curve that time itself slows down near its edge. To an outside observer, someone falling into a black hole would appear to freeze in time at the event horizon, while the person falling would experience time normally and vanish into the void. This extreme time dilation means black holes may offer a strange connection to time travel. While we can't use them to go back in time, their gravity does affect time in such a way that makes futuristic effects possible. However, anyone attempting to enter a black hole would be torn apart by tidal forces long before reaching the center. This process, known as spaghettification, stretches objects into long, thin shapes due to the intense difference in gravity between their top and bottom. Yet, not all hope is lost inside a black hole. Some scientists believe that at the center of a black hole, instead of a singularity, there may be a bridge to another region of space-time, a wormhole. If such a thing exists, it could potentially link two distant parts of the universe, or even two separate universes entirely. Though it remains purely theoretical, the mathematics behind wormholes is consistent with Einstein's equations. The challenge is finding a way to stabilize such a structure and survive the journey. The information paradox is another mystery surrounding black holes. According to quantum mechanics, information about matter cannot be destroyed. But when matter falls into a black hole, it seems that all the information about its composition is lost forever. Stephen Hawking proposed that black holes may emit a faint glow, now called Hawking radiation, due to quantum effects near the event horizon. Over time, this would cause black holes to evaporate completely. But what happens to the information? Is it destroyed or somehow encoded in the radiation? This paradox has baffled physicists for decades and remains one of the most important unsolved problems in theoretical physics. Black holes are also cosmic engines. As matter falls toward them, it heats up to incredible temperatures, releasing powerful jets of energy. These jets can be seen across billions of light years, outshining entire galaxies. In some cases, they regulate star formation in galaxies, shaping how they grow and evolve. In this way, black holes are not just destructive. They are central to the life cycle of galaxies and the cosmos. In recent years, black holes have gone from theoretical monsters to observable phenomena. In 2019, astronomers captured the first ever image of a black hole's event horizon, located in the galaxy M87. This image showed a glowing ring of hot gas orbiting a dark center, confirming decades of predictions. Gravitational waves, ripples, and space-time caused by collisions between black holes have also been detected by observatories like LIGO, offering a new way to study these invisible giants. Despite these breakthroughs, black holes remain a frontier of human knowledge. They challenge our understanding of reality itself. What lies beyond the event horizon? Is the singularity real or just a mathematical artifact? Can we truly unify general relativity with quantum mechanics to describe what happens inside? What we do know is that black holes are not rare. They're scattered throughout the universe, millions, perhaps billions of them. And while they may seem alien and distant, they are connected to us. Some of the heavy elements in your body were forged in the supernova that created a black hole. They are not just destroyers. They are creators too, shaping galaxies and enabling life. Black holes remind us of the limits of our understanding and the potential for discovery. They're the ultimate test of physics, where space, time, energy, and matter meet at their extremes. And though we cannot see them directly, they pull on our curiosity just as they pull on light, demanding that we continue our journey to understand the universe. The universe had a beginning, but will it have an end? That question haunts scientists and philosophers alike. As we look out into the cosmos and study its structure, we also look forward in time, try to understand how it will all unfold. Will the universe expand forever? Will it collapse in on itself? Or is there a stranger, darker fate awaiting us? To answer these questions, we must first consider what drives the universe today. Ever since the Big Bang, the universe has been expanding. For a long time, scientists believed this expansion might slow down due to gravity. But in 1998, astronomers made a shocking discovery. The expansion is actually speeding up. Some unseen force, is pushing galaxies apart faster and faster. This mysterious force is known as dark energy. Dark energy makes up nearly 70% of the universe, yet we know almost nothing about it. It behaves like a constant pressure that counteracts gravity on cosmic scales. If dark energy continues behaving the way it does now, the universe is headed for what scientists call the Big Freeze. In this scenario, galaxies will move farther apart, stars will burn out, and the universe will become a cold, dark, and empty place. Over trillions of years, all stars will die, black holes will evaporate, and even atoms may decay, leaving behind a lifeless void. But that's just one possibility. Another theory suggests that gravity might eventually overpower dark energy. In this scenario, the expansion slows down, stops, and reverses. Galaxies will begin to draw closer, stars will collide, and the universe will collapse into a fiery, dense state. This is called the Big Crunch. It mirrors the Big Bang, but in reverse. Everything would end as it began, in a singularity. Some even speculate that such a collapse could lead to another Big Bang, creating a new universe in an eternal cycle of birth, death, and rebirth. Then there's the most violent scenario, the Big Rip. This happens if dark energy becomes stronger over time. Its repulsive force would eventually overcome all forms of gravity, and even the forces that hold atoms together. Galaxies would be torn apart, then solar systems, then planets, then the atoms themselves. Time would stretch infinitely, and space would be shredded. The universe would be ripped apart on every level, ending not with a bang or a whimper, but a tear. Each of these fates depends on the true nature of dark energy, something we haven't yet fully understood. New telescopes, surveys, and experiments are being launched to study it more closely. The answers may reveal not just the fate of the cosmos, but the deeper structure of reality itself. There are also more exotic ideas. Some physicists propose that the universe could transition into a lower energy state, in a process called vacuum decay. If this happened, a bubble of true vacuum could expand at the speed of light, obliterating everything in its path. We wouldn't see it coming. One moment, everything would be as normal. The next, existence would be rewritten. Others speculate that we might be inside a simulation, and the end could come if the program is shut down. While this idea belongs more to philosophy than science, the fact that it's even discussed shows how open our minds must be when grappling with the universe's ultimate fate. Despite the unknowns, one thing is clear. The universe is changing. It's not static. Every second, it evolves. Stars are born, galaxies move, entropy increases. And we, for the briefest flicker time, are here to witness it. Our lives are short, but our minds can stretch across billions of years and light years, imagining the past and the far future. The end of the universe, whenever and however it comes, will be a moment of profound transformation. Whether it ends in cold silence, fiery collapse, or chaotic destruction, it will mark the close of one cosmic story, and perhaps the start of another. Until then, the universe continues to unfold its mysteries, and we continue to ask the biggest questions. Why are we here? What is all this for? And what happens next? From the fire of creation to the silence of the void, the universe tells a story both ancient and infinite. And though we are just a flicker in cosmic time, our curiosity might just be the light that reveals the next great truth. Backhand index pointing right. If you want more journeys into the unknown, share, and subscribe to History Vault. Because the universe isn't done telling its story, and neither are we.